Hi everyone, thank you for watching this presentation with the following title, The Use of Additive Manufacturing of Building Components. The development of man and the search for answers to the continued survival of society is significantly contributing to the need to change the way we think. Construction industry is one of the main energy consumers, being responsible for the emission of high percentage of carbon dioxide. In this sense, society and designers need to embrace the challenge of defining solutions consume less energy and natural resources. The search for new emerging solutions aims to stop the continued expansion of architecture using non-renewable energy. With the use of highly abundant materials in our ecosystem, we intend to change a continuous closed cycle through the contemporary diversion of living materials, implementing it in the additive manufacturing of constructive systems. When this ceases to be functional, the object will be to return it its natural state through the possibility of biodegradation, promoting the growth and reproduction of new living materials. Wood is the most important raw material in the evolution of man. Cellulose is the most abundant polymer in nature, and it is a natural material, biodegradable and recyclable. To produce a cellulose-based mixture, it is necessary to have a base, a biopolymer, a solvent, a bioplasticizer and additives, if necessary. In order to test the viability of the mixture and to perform a comparison term between them, 5 different recipes were developed. These mixtures vary according to additives, sawdust, coffee ground, kiwi and potato peels. To prepare each mixture, it is necessary to carry out a set of actions. This video shows the process of extrusion with a cellulose-based mixture. A fluidity of the mixture enhances the final printing quality of the elements. To verify the viability of the mixture, a set of initial tests was carried out. The first consisted of checking the maximum degree of curvature supported by each mixture during extrusion. In this way, 4 specimens were produced with different inclinations, between 10 and 40 degrees. All mixtures achieved the same results, supporting maximum printing inclination of 30 degrees. A second test aimed to analyze the maximum degree deformation, retraction, delamination, and loss of water volume after drying. 3 identical specimens were produced and the results analyzed. In this table, it is possible to observe that the shrinkage of the pieces is higher in mixture with additives of higher granulometry. The particle size of kiwi and potato is superior to sawdust and coffee grounds. The kiwi-based mixture has a 52% retraction, while sawdust is 24%. Looking at this picture, we can clearly see the color change is caused by the addition of natural fiber. It is also possible to observe that the deformation and delamination was created in the mixture C1 compared to C2 and C3. A column system composed by staves with different heights and configuration is conceived within the help of computational designing tools. The purpose was to test the use of compositive materials developed for the manufacturing of the column parts. Each stave consisted of an external membrane that has a regular central undulation, a simple interior wall strictly structural, and finally an internal structure in V-like shape connecting the finishing wall of the object. For the geometric definition of the shape of the components, a parametric model was developed for the customization of each component, namely the variation in A and the radius of the shape, the number of points and the amplitude of each undulation, the number of divisions of the inner walls that allows the union between them. A piece to be printed using the PEM technique with coffee-based mixture. Pieces produced still wet, left piece sawdust-based mix, central piece coffee-based mix, right piece cellulose-based mix. After the first printing test, we came to the conclusion that it was necessary to optimize the printing method, as they are mixtures based on natural materials and when subjected to drying, the water evaporates and causes deformation and lamination between layers. Placing the stitches in the same place causes an excessive accumulation of paste, as you can see in the picture. As a way to correct this problem, a set of variable stitches was defined in the G-code. The optimization of the G-code allowed to decrease the deformation and delamination between layers to be lower, increasing the final quality of the pieces. The research allowed to conclude that the use of cellulosic materials in conjunction with the use of AM techniques has the potential to develop constructive systems. The use of these materials effectively creates more sustainable, ecological, and reusable systems. The use of additives or natural fibers in the recipe determines the degree of fluidity of the mixtures as well as the final result of the desired object. The introduction of natural fiber aims to reduce the retraction and elimination between layers. I am currently exploring the possibility of using this material for formwork for custom building elements. We want to acknowledge Lab 2PT from Minho and FCT for their institutional and financial support of the research, also Raiz for supplying cellulose. Thank you.